actually. You know, just in case you didn't look at it, our exam is not until next week. And in case you didn't bring your flammability diagrams, I printed some more, so here, I'll send them. I'll send them.
This is a flammability diagram, I guess.
Whatever.
Okay,
this one actually has triangles inside. Look at that. You don't even need to, you don't even get to use
so
them.
we're asked if we have
yeah.
methanol, okay, stored in a vessel. So you might have a gallon-sized jug of methanol, right? You wouldn't necessarily, right, inert that. The question is, would that, if the vapors escape, would they be flammable? In this case, right, we'll look at both. So we'll look at that. If you have a gallon-sized jug of methanol, is it flammable? And then let's inert it and see what happens. So the first thing to figure out if it's flammable, right? We need to go look at the flammability limits. Okay, so go to appendix. I think it's table 80. I didn't write it down here. So the lower flammability limit is 7.3%. Okay, and the upper flammability limit is 36%. Okay, let's compare this to methane, right? The upper flammability limit for methane was about 7.1, if I'm not mistaken. I didn't write it down, but it had a lower flammability limit about 1 point something, 1.4, if I'm not mistaken. Okay, so clearly it's easier to be below the lower flammability limit for methanol, but it has a pretty significant flammability zone. Right, from 7 to 36%. So we're going to see what that does to our flammability diagram.
So if you had, say like methane, you're worried about igniting, so it's like at 6%. Could you flood the area with methane to try and stop it from igniting?
Yes, you would. So the question was, can you flood the area with methane? Yes, you can, right? But you're only secure in that area, right? Because then your methane is going to disperse, and at some point now you have a much wider area where it's actually in the flammability zone, and you're gonna, right? It's gonna ignite over there and then work itself back. So you know, to be honest, right? You can be outside of the flammability zone because you're above the upper flammability limit, but you're not safe. That's not where you want to be. The only safe place is to be below, right? Truly, to be truly safe. Okay, now for this problem, right, and for our flammability diagram, we also need the limiting oxygen concentration. Okay, and that is 10% according to table 6.2. Okay, if it's not given in table 6.2, you know that you have a few equations in the book that you can use to estimate the limiting oxygen concentration. Okay, so that's the concentration of oxygen below which you're safe because there isn't enough oxygen for the fuel to burn. Okay, so it's going to be a little bit different for different compounds, right?
Just in that well.
And then I believe we look, so, sorry, what was that?
Nothing.
No, okay. I know we, very quickly, we looked at the stoichiometric concentration. Okay, and we might have, went over that very quickly. So we have methanol completely oxidizing to CO2 and water. Okay, so for, we get one CO2 and 2 waters, we have one, so it's like 3/2 of oxygen. So depending on what we're looking at, our Z value, if that's what we're looking for, that's oxygen concentration over methanol. I don't know that I would put it that way. Let's just calculate the oxygen concentration instead. Because that's so oxygen, right? So the oxygen concentration, stoichiometric oxygen concentration, that would be at 0 nitrogen, when we only have methanol and oxygen, it would be 3/2, 1.5, 3/2 plus 1, and that is 0.6. So that would be, in other words, 60% O2. Okay? And really, for this problem, you are not asked for the entire flammability diagram. So this would be sufficient actually for you to set up that. So we need one more point to really define the entire flammability diagram, and that's the upper oxygen limit. Upper oxygen limit. Because the lower oxygen limit is, we usually leave it approximately equal to the lower flammability limit. There is a table though where you should go and look for data first. And I can't remember if they're given for methanol or not. I've not written them down, so I'm thinking that it's not. If we need, maybe I should, so for this particular problem, we don't need the upper oxygen limit, but for completeness, let's just put it on there so that, practice one more time how to do it. So upper oxygen limit, we have to, if it's not given in the table, we have to use this equation, COUL, 100 minus UFL. You see this over here? Barely over UFLO, which is the oxygen concentration at the upper flammability limit. Plus UFL 1 minus COUL. So UFL, we have there, it's 36%. So UFLO then is 100 minus 36 times 21%. So UFL oxygen is 13.44. So, and this coefficient here is given in the book as negative 1.87. So our upper OL is equal to 36 times 100 plus 1.87. 100 minus 13.44 over 44 plus 36, 1 plus 187. Okay, obviously an empirical formula. Our UOL, upper oxygen limit, is equal Okay, and the key to remember is that upper oxygen limit is fuel concentration. Fuel. Okay. If you accidentally put it as oxygen concentration, it should be evident on your diagram that it's wrong. Right? Your diagram is usually looking like a triangle, right? If you have something that looks like this, you probably have put that in the wrong spot. Okay. Yes.
Where does this equation come from?
So yeah, that's a good one. That's a good question. So I have no idea how they came up with that equation. I didn't write down the equation number that's in the book, but you know, they fitted something.
Can you empirically solve for it using a relationship between reaction quotients, concentrations, and gives energy until it would be spontaneous anymore?
You know, I don't know. I would have to look to see how they derived it. But there's a chance that there is some combustion, right? Kinetics and stuff in that correlation right there. But I don't know on top of my head how they, I didn't go back. The authors of the book weren't really, right? They were just saying that this comes from data that has been collected for a number of hydrocarbons. So that's another thing to keep in mind, right? What that COUL, that coefficient there, it's derived from something very specific, right? Hydrocarbons. So if you have a flammable liquid gas that is not hydrocarbon based, then you can sort of question whether that's a good approximation. But it might be better to have a value, right, ballpark, than not to have anything. Most of the time though, what we're really looking at is we have a container that might be inerted or not, but it's vented to air. So, excuse me, really what we are interested in is this airline and anything that's to the right of it. So, here we've done this a few times now. 1, 2, maybe we've only done it once. In terms of how to draw the flammability diagram. Yes.
Where did you get the 1.87 for COUL?
It is given in the book, but it is not, it's in the text under the equation. So just bear that in mind, right, when you're on the exam looking for it, that you need to know where to find it, but it's next to the equation.
Okay.
Right? But it's not like part of the equation box or anything. It's given and it's stated that it's derived for hydrocarbons. Okay, so usually, I don't think I have had a single year where I haven't had a flammability diagram on the exam. So this is an important one to handle.
What's the 0.21?
With the 0.2, oh, that's, so it's the oxygen concentration at the upper flammability limit. It's 36% of methanol in this case in air. So that's 100 minus 36. 36 is the air concentration, and then we get into oxygen. So we need the oxygen concentration. That's what that O stands for. So we're just assuming that 21% oxygen in air. So that's what that's coming from. Okay. Procedure for the flammability diagram. I am having problems saying flammability. I'm gonna go with LFL, so I don't have to say it. You all right. Draw the airline. Mark LFL and UFL on the airline, because those two limits, these are fuel concentrations in air, these two, LFL and UFL. So 7.3 LFL, 36% is UFL. And then the next thing I normally draw is the line, LFL to LOL. That's just a straight line because at constant fuel concentration, we approximate those. You might find an LOL in the table, but very few is given in the table in the book. Okay, then next, I can't remember if I put the stoichiometric line first or mark the UOL. So for this specific problem, we actually don't need UOL, but you want to put, just for completeness sake, we put it on there so we know the entire flammability diagram. UOL is 80.7%, but it's fuel. So fuel X is about 81, but it's on the zero nitrogen. Okay, it's upper oxygen limit, so it's fuel in oxygen. Yes.
Quick question. You wrote that the LOL is 10% from table 6.2. Are we just neglecting that and saying the LOL is approximate?
Wait, LOC.
Oh, that's LOC?
LOC.
Okay.
Oh,
Sorry, my bad. LOC. I know, you can, yeah, this is LOL. Okay. So if we need the entire flammability diagram, we need UOL, and then we connect that point with the upper flammability limit. And next, we put the stoichiometric line on there. So we needed the stoichiometric concentration to put that on. That one goes from the stoichiometric concentration down to 100% nitrogen. We calculated that it's 60% oxygen. So that would be here, and we draw a straight line to zero down here. Okay, we need this to make sure that we're interested in this corner here. Okay, the next thing is LOC, the limiting oxygen concentration. It was 10%. If you can find this value in the book, right, you don't have to calculate it. You can just say that's what I'm using, unless you're of course asked for it. And so if you're asked for it and said, okay, calculate the LOC, right, using this equation, and then you get that, if you calculate it, it's 12%. Which number would you use? Which is safer? The lowest one, that's right. And possibly this is more accurate because it's the experimentally determined one. The other ones from your equations are estimates, right? Okay, so the next thing we do is mark this corner here. And here's where I want you to pay attention. I want you to use, I think it's method 1, okay, in the book to determine the flammability limit in air. Because I feel this is more accurate. There are a few more ones given in the book, but I want you to use method 1. Okay, so basically the point we're going to mark at the corner here is where LOC is crossing LFL, the LFL-LOC line, LFL-LOL line, right, in that corner. Or the stoichiometric line, whichever gives you the larger flammability region, really is what you should be using. Because then what you do is you connect that to the UFL line, and this little corner here, this one here, is your flammability limit, or your flammability zone in air. Okay, that's all you needed. So you didn't really need to put UOL in for this specific problem, but we did that for completeness sake. So if you ask for the entire flammability zone, the entire one,